All right, so we're recording. Welcome back, everybody. This is the start of week 9 of the semester. We're almost halfway through. So just a few reminders about what's coming up. First of all, we have homework number 9, which is not going to be due for another 2 weeks. So it's going to be due on Monday, 2 weeks from now. That's the 21st of March. That's after we come back from spring break. Remember, next week is spring break, so I don't expect you to turn anything in during spring break, but the day we come back, that's when this will be due, okay? And it's a pretty standard length assignment, so you'll have 2 weeks to work on that. The other thing to note is I did mention that there would be a quiz coming up this week. However, since we have a lot to get through in the lecture, I decided to make this a take-home quiz. So you can get a copy of the take-home quiz up here at the front of the room. It's on capacitors. The whole problem is you look at this network of capacitors and you solve for the unknown charges. So it's pretty straightforward, something you've been doing for a while. That's going to be due Wednesday of this week. Okay, so turn that in along with homework number 8 on Wednesday of this week. Any questions on that? All right, so if there are no questions, let's get to the next lecture. So the last thing we talked about was chapter 8 of volume 2 of the textbook, which covered capacitors and this idea of capacitance. There's another property that's commonly found in electrical circuits called resistance that we want to understand. And we also want to get an understanding of electric currents. So we don't want to just be thinking about charges that are stationary and not moving. Instead, we want to get a handle on how to treat moving charges in an electrical circuit. So that's what we'll do in this chapter. We'll finish this by the end of the week. It's a pretty short chapter. Okay, so the first thing I want to discuss is batteries and electric current. We've been using this idea of a battery in some of the problems that we've been solving up to this point, but I really want to not just gloss over the details and say a battery is a source of voltage. Let's actually think about what's going on inside of a battery, what sort of chemical reactions are present, and how does that lead to the battery being a voltage source, okay? So that's what we'll get into here. All right, so what is an electric battery? Fundamentally, you can think of a battery as a device that's converting chemical energy into electrical energy. So there's some energy that's stored within the chemical bonds of some material that is later converted to electrical energy in the form of charges moving around in the circuit. That's what it's doing. And there's a basic design that pretty much every battery follows, which is you have your electrodes and you have your electrolyte. So let's define each one of these terms. So your electrodes are 2 different metals, okay? The 2 metals that make up your electrodes have different properties. One of them tends to readily accept electrons, while the other one tends to give up electrons. So as an example, what you see here, the 2 electrodes are zinc and copper. That would be a good example of 2 different electrodes with these different chemical properties. Now, the electrodes themselves are immersed in a liquid or sometimes a gel, which we call an electrolyte. And the electrolyte is basically something that's there to conduct ions. So either positive ions can be moving through this electrolyte or negative ions, depending on the situation. And what I'm going to try to show you over the next couple slides is that there are chemical reactions happening inside of this battery when it's designed in this way that lead to it having a potential difference or a voltage across the electrodes. So once we establish that it has a voltage across the electrodes, we can hook it up into a circuit and it can do all sorts of things like charge a capacitor or maybe drive a current, things like that. Okay, so for the example that we're going to go through in some detail, this is going to be our design. We have a zinc electrode, we have a copper electrode, and these 2 electrodes are going to be sitting inside of a sulfuric acid or H2SO4 solution. Now, just so you're aware, there are a lot of different sorts of chemicals we can be using for a battery. This is just one example, but this example will illustrate the basic way a battery works. Okay? So, what I'm going to show you now is kind of an animation illustrating the chemical reactions that will happen when you put these 2 electrodes in the electrolyte solution And hopefully you'll be convinced that at the end of this, we have a voltage across the terminals, okay? So let's start with this. H2SO4 is a molecule that, when placed in water, tends to dissolve in this sort of way. It dissolves into two hydrogen ions, which each have a positive charge, and an SO4 ion, which carries a charge of -2. Okay, so overall, there's no charge here, but when it dissolves in water, we end up with these two positive ions and this one negative ion. Okay? All right. So what's going on at the zinc electrode? Let's take a look at that. So again, zinc is an atom which is overall electrically neutral. However, it tends to leave behind two electrons on this electrode when placed in the solution. So we get positive zinc ions with a charge of +2 coming off of this electrode, leaving behind two electrons on the electrode. Okay? And clearly you can see now we have some negative charge on this zinc electrode. Right? Let's take a look at what's going on the copper electrode. So when you put the copper electrode in this solution, this is what tends to happen. The copper electrode tends to give up two electrons to the solution while leaving behind a positive copper ion with the charge of +2 on this electrode. Okay? Now that's not the end of the chemical reactions. Let's just take a look at what's going to happen. If I have just an electron sitting in this solution and a positive hydrogen ion sitting in this solution, they'll tend to group up. Okay? So here's what that looks like. Actually, let me give you this one first. The positive zinc ion and the negative SO4 ion, those tend to group together to form ZnSO4. This is a neutral molecule. And then the two hydrogen ions and the electrons tend to group up together to form H2, which is a gas that just bubbles out of the solution. Okay? So that's kind of a long chain of events. There are a lot of different chemical reactions that are occurring there, but here's the end result of that. You have on the zinc electrode some negative charge, and on the copper electrode some positive charge. Okay? So we have a negative side and a positive side of this battery, and quite literally that's the positive and negative terminal that you see on any standard battery that you buy at the store. Okay? So one of them has a negative charge on it, the other has a positive charge on it. Does that make sense? And because of that, there's a voltage across the two terminals because of this charge accumulation on each one of the electrodes. So again, here's what's going on. You have these two electrodes. You put them in this solution, which we call an electrolyte, and all kinds of chemical reactions are happening when you put the electrodes in the electrolyte solution. But at a certain point, you reach what's called chemical equilibrium, where the reactions stop. Okay? And once that happens, as we said before, you have a negative charge on one of these electrodes and a positive charge on the other. So just as a way of naming these things, we sometimes call the negative electrode the anode and the positive electrode the cathode. I don't tend to use that terminology, I just call it positive and negative, but this is something you might see in a textbook or other sources. All right, so when we establish this positive and negative charge on each side of the battery, that establishes why we have a potential difference. Okay, we've gone through a lot of different examples of situations like this where if you have a negative charge on one side, a positive charge on the other side, there will be some kind of potential difference between those two sides. And it's important to note how the sign of the potential difference works. So whether it's positive, whether it's negative. This is how it works. The potential difference will increase if you're going from the negative terminal to the positive terminal of a battery. And if you're going in the opposite direction, the potential difference will be negative. Okay, so it's positive potential difference, positive delta V, if we're going from the negative to the positive terminal of the battery. And it's a negative delta V if we're going from here to here. Does that make sense? So that's just how the sign works. Okay, oftentimes, and in fact you saw this in the last lab, right, with capacitors. If you connect batteries together in series, you'll effectively just add their voltages together. Okay, so for example, this is what it would look like on a circuit diagram with N batteries connected together in series. So I've shown you this kind of symbol before, right? If you see this symbol where we have a short line and a long line, that denotes a battery. The short line denotes the negative terminal. The long line denotes the positive terminal. So what I'm showing you here is N of these things connected together in series. So if we think about point A and point B and the potential difference across A to B as the total potential difference across these series combined batteries, that's just going to be V1, the potential difference across the first battery, plus V2, potential difference across the second battery, plus V3, and so on, until you get to the last one. So basically, connecting batteries in series, you're adding their voltages together. Make sense? Any questions so far? Okay, now before we get to this, I'm going to show you just a really quick demo. So this is an example of a pretty crappy battery, but it's actually doing what we want. It's creating a potential difference across the two terminals. Here, I have a piece of copper wire and a piece of zinc wire. And these two wires are placed inside of an orange, which has a bunch of sulfuric acid in it. And that acts as our electrolyte. These are the two electrodes. The electrolyte is the sulfuric acid inside, or the, citric acid inside of this piece of fruit. And as you can tell, I've hooked this up to a voltmeter. This is measuring in millivolts. So it's only about 24 millivolts, so not that impressive, but you see the principle in action here, right? We get a potential difference across these two electrodes when I set up the battery in this way, okay? So, with that said, here's what we've established so far. We understand the basic design of the battery and how there's a positive electrode and a negative electrode and a potential difference between the two electrodes. Now let's talk about electric current, how if we connect that battery to something, let's say a light bulb or some other type of device, it will drive a current. Let's try to get an understanding of how current is flowing when you connect a battery to some device. Okay, so we have the same basic picture where we have a positive and a negative electrode immersed in some type of solution, which we call our electrolyte. But now let's imagine connecting those terminals by some kind of conducting path. So maybe we take a piece of copper wire, connect it to a bulb here, and then another piece of copper wire to connect it back to the electrode here. And now what we have is a circuit. This is what we call a circuit because everything is connected in a continuous loop and charge is able to move in a loop either clockwise or counterclockwise. There's a path for that to happen, okay? So let's take a look at kind of the details of how that would work, given that we know electrons are what are moving around inside of a conductor, okay? So let's consider this. We have our negative electrode, okay? And that's connected to this piece of wire. And presumably, there are a whole lot of free electrons within that piece of wire. What are those electrons going to want to do? They're going to be repelled away from the negative electrode, right? Because if there's a negative charge here, electrons are going to move away from it. They're going to move through the light bulb, and they're going to be attracted to the positive electrode, right? So you get a sense that electrons would be moving this way. Okay? Then there's actually something happening in our electrolyte solution. There are a bunch of ions in here, which continue carrying the current through that solution and then back to the negative electrode. So current is moving in a loop like this inside of this setup. And as long as we can continue these chemical reactions in the battery that I showed you before, charge can just continue to move as long as that's the case. But in reality, we know batteries don't last forever. Just give me a second. Batteries don't last forever. Eventually, either the solution will be used up or the electrodes will be used up and we'll have a dead battery. In a rechargeable battery, by the way, you can reverse the reactions so that everything can be reversed and they can happen all over again. What was your question? What?
You answered my question.
Okay, good.
I was wondering, I know that like even with rechargeable batteries, like everyone knows on an old phone, the battery gets progressively less and less charged.
Yeah, so it's not perfectly reversible in that case. There's some like permanent degradation that will happen, but the point is you can do it for a good number of cycles before that permanent degradation happens. Okay, so I'm going to show you another sort of animation. Again, I'm just going back to the same example with the zinc and copper electrodes in the sulfuric acid solution. But if you had a different sort of chemistry, the same basic idea would hold. So what I want to give you a sense of is how are charges moving around within this circuit, okay? And I'm only going to show you a small sample of those charges. So we already established, right, that we should have an excess of electrons on the zinc electrode, right? So I just want to follow what happens to these two electrons as we sort of follow their motion around the circuit. And then you can just scale this up because this is happening to some gigantic number of electrons, okay? So here we go. Start with the two electrons on the zinc electrode. And then remember that inside of the solution, we have this dissolved molecule, which gives us positive hydrogen ions and negative SO4 ions. As we said, the electrons are going to be repelled away from the negative electrode, which will force them to move through the bulb to the positive electrode here. Once they make it back into the solution, they're going to combine with the H+ ions and bubble out like this. Okay? And then that process will repeat all over again. So let me just show you again because it kind of happened in animation faster than I could explain. So electrons repelled from here, move around the circuit, back into the solution, combine with the H+ ions, creating H2 gas. Another zinc atom will be pulled off the electrode, and that process will repeat. Okay? And that can repeat as long as those chemical reactions can happen in our solution.
So what do rechargeable batteries do to reclaim the hydrogen that's lost in the bubble cells?
So this would not be a good example of a rechargeable battery because that hydrogen is gone. So you'd have to have a different chemistry for that. Yeah.
So eventually the zinc can run out, or is that what it is?
Yeah. So again, in this specific case, we're going to just permanently lose hydrogen to gas that bubbles out of this battery. So yeah, at a certain point, all the chemicals that are available for these reactions will be depleted. So this has a finite lifespan. All right. So let's talk about electric current then. Let's define what this is. So in a rough sense, electric current just refers to the motion of charge through a circuit. But in particular, electric current given by capital I is the amount of charge per unit time that's moving through some cross section of your circuit. Okay? So what I want you to think about right here is, let's say we have a wire, some kind of conducting wire, typically going to be made out of copper in a typical circuit. And if there's current running through this wire, we're going to have charges moving across it. Okay? So when I refer to a cross section of that wire, I want you to just imagine we take a little cut across the wire this way. And typically that's going to be a circular cross section because wires tend to have a cylindrical shape. And we're just asking the question, every unit time t, how much charge is passing through here? Okay? When I take the ratio of that charge to the amount of time that passes, that's going to give me the rate for those charges moving through, and that's my current. Okay? So average value of the current in some time delta t is delta q, the amount of charge that's moved past here, divided by delta t, how long it took to move past there. Now, like with any kind of rate like this, we can define an average value, which is delta Q over delta T for some kind of finite time interval delta T. But if I take the limit where delta T goes to 0, this becomes a derivative. And this is now dq dt. So this would be an instantaneous value. The difference between these two is the average value is the average over some time interval. The instantaneous value is what is the current right at this specific moment in time. Okay? So now let's take a look at the units. Well, if you just take a look at the definition, it should be pretty clear what the units are. Right? What do we use to measure electric charge in the SI system? We use coulombs, right? And then time, what's our standard unit? Seconds. So it stands to reason that our SI unit for current should be a coulomb per second, right? So that's what we call an ampere, or sometimes amp for short. 1 amp is defined as 1 coulomb per second. Okay, so if we have a circuit, and then this is the simplest example of a circuit that I could probably show you, where we just have a single battery hooked up to a single light bulb, right? What I want to show you is if we have a single conducting path where everything is connected, at every point in that circuit, the current will be the same. Okay, so let's take a look at, let's say, point A, point B, and point C within this circuit that I'm showing you here. My claim is that the current at point A is the same as the current at point B, is the same as the current at point C. There's a pretty simple reason for that. Okay? If that were not the case, that the currents were the same at all these 3 points, then what would be happening is charge would be building up at some point on this wire, right? Because let's say, there's more current going into point B than coming out at this end. What would be happening is charge would be accumulating here at point B. That's not what's happening. Charge is merely moving around the circuit. It's not accumulating at any given point. Therefore, the current is the same at every point. Okay? So I want to just give you some practice using this definition of current. Let's say that in a wire, we have a constant current of 2.5 amps. So over the course of 4 minutes, how much charge passes through a cross-section of that wire? And then after you've answered that, approximately how many electrons does that correspond to given the charge of an electron, 1.6 10 to the minus 19 coulombs? So take a few minutes to try to work this out, and we'll go through it together. All right, what are we getting for this? How much charge?
600 coulombs.
600 coulombs, that's right. If you're not sure how that goes, let's work it out real quick. So here, we're just applying the definition of electric current, which is I equals delta Q over delta T. And then what we're trying to solve for is the amount of charge in a given time interval. So delta Q is I times delta T. So in this case, our current is 2.5 amps. And then we'll remember, what's the equivalent unit for an amp? That's coulombs per second. So our time is 4 minutes, but we better convert that to seconds. So 4 times 60 gets us to units of seconds. So this is the calculation you do to get 600 coulombs. Okay, pretty straightforward. So now let's take that amount of charge and convert it to a number of electrons. Because the idea would be, remember, what we just found is that in this piece of wire, every 4 minutes that passes, you have 600 coulombs of charge going through a given point of this wire. So we can convert that amount of charge to an equivalent number of electrons, and that's quite literally how many electrons have passed by that point in the 4 minute interval. So we have 600 coulombs. 1 electron has a charge 1.60, 10 to the minus 19 coulombs. We're just counting up electrons, so we don't have to worry about the sign here. Okay, what does that work out to?
3.74 times 10 to the 21 power.
3.74, 10 to the 21 power. We'll want to round that to the 2 sig figs here. Okay. So something like 10 to the 21 electrons. Very, very large number. All right, any questions on how we did this? All right, sounds good. Let's keep going. Okay, so I now have to tell you about conventional current. This is, how do I explain this? Kind of a historical artifact, okay? If the way we decided to describe electric current was formulated today, we would probably do this in a much different way, but this is a convention that's been established for a very long time, and it's kind of too late to change it. So for example, in the US, we don't use the metric system, right? We don't use meters to, measure distances and things like that. We have this kind of outdated system of units. But guess what? There's so much infrastructure that's built up around our system of units that realistically we're never going to switch over, right? Kind of similar idea here with conventional current.
Yeah, this is why you said that, like in the very beginning, that the positive and negative charges are actually should be named the opposite way.
Yeah, this is what I'm getting at here. So, all right, so electric current was studied, a pretty long time ago. There were people building rudimentary circuits as far back as the early 1800s. And keep in mind, this is long before we had a solid atomic theory of matter. We didn't understand at this time, in the early 1800s, that matter was made out of atoms, and that atoms were fundamentally built out of protons, neutrons, and electrons. None of that picture had been established yet, okay? So we did know that there was something flowing around in a circuit when electrical current was present, but at that time we had really no idea what it was made out of, okay? That didn't come until much later. The early 1900s is when we really got a good understanding of the structure of an atom, okay? So back then, it was assumed that it's positive charges that move around when you have current in a conductor. Let's say in a wire that has some current flowing through it. It was just taken for granted that positive charge is moving around. We now know that is not the case. We know it's electrons that are carrying the current, but we still use that convention. In other words, the convention, when we're describing electric current, is to act as if positive charge is what's moving around, even though we really know it's negative charges, electrons, that are carrying the current. Okay, and that's just because it was historical precedent that had been set. A lot of work had been done, and it was sort of too late to switch things over at a certain point. So this is what we call conventional current. Conventional current is the direction that positive charges would move in a circuit. Okay, so here's the picture you should have in mind when it comes to current. Let's say, again, let's take the simplest possible circuit. We have a battery here connected to a light bulb. Okay, this is the positive electrode, this is the negative electrode of that battery. So we have a good sense of how electrons should be moving within this circuit, right? If this is my negative electrode, for example, electrons will be repelled from that, so they'll move this way throughout the circuit. In this particular circuit, we would have electrons moving in the counterclockwise direction. Does that make sense? So that's shown in red here. The conventional current, however, just goes the opposite way. Because it turns out negative charge moving this way is the same as an equivalent amount of positive charge moving in the opposite direction. And that's the idea behind conventional current. We really know it's negative charge moving this way, but just for descriptive purposes, we act as if it's positive charge moving the other way. Those are equivalent mathematically done.
I got a question. It might be out of the scope a little bit, but if you have a battery connected to something and instead of grounding it to the battery, you ground it to something else, are you pulling electrons from that source of ground then? Or do we just label the plus and minus backwards?
I guess it would depend on exactly what you're connecting it to, but what are you talking about? The plus and minus signs we use here, or?
I'll talk to you.
Okay, yeah. So takeaway point here of conventional current is, again, it's a convention we adopted a very long time ago, and we still use it to this day, even though it's, strictly speaking, kind of wrong. Because really what we know is electrons, negative charges carry the current. Okay, go ahead.
I know it's a bit of a loaded question, but why is it that the flow, like the current change of it, won't affect like a device working, for example?
So there are some instances where there is a difference between having a positive and a negative charge flowing through your circuit. In particular, if you look ahead at the Hall effect, which is in chapter 12, you'll see an example of that. But for the rudimentary stuff that we're starting off with, there's really no difference between negative charge flowing one way and positive charge flowing in the opposite direction, just as a description of the current. Okay. Okay. So the next thing we want to establish here is, how do currents relate to E fields? We've spent a whole lot of time calculating electric fields and coming up with different methods of doing that. And one thing that you should always be keeping in mind here is, if you have an electric current in a circuit, if charge is moving around, the reason for that is you have an electric field which is pushing those charges around. You're not going to have a current without an electric field present. So I want to give you some sense of what that electric field looks like in this type of circuit where we have just, again, a battery connected to a light bulb, probably the simplest setup you could think of. Okay, so first of all, remember, in a battery, we have a positive and a negative terminal, and quite literally, there is positive and negative charge built up on each one of those terminals. And when that's the case, we're certainly going to have an electric field present, right? If we have positive and negative charge separated out. Generally speaking, what direction does an E field point in when it comes to positive and negative charges? Okay, so E field comes off of positive charges and goes towards negative charges, right? That's happening inside of the battery. And it's also happening, as it turns out, within the wires that connect that battery to our device. So here's what it looks like inside of the battery. You're going to see E field lines coming off of the positive terminal and then terminating at the negative terminal of the battery. Okay? But that's not all, right? Because if we have charge moving through these wires that connect our battery to our device, we're also going to have an E field there as well. So this battery, which has its own E field, when you connect it along a path to some device, is going to set up an E field within those wires that connect it to that device. And the details of how this works, by the way, are super complicated, kind of beyond the scope of the class, but I put a little lecture supplement in the lectures folder on Canvas where I try to explain how these E fields do get set up in this way. You can take a look at that if you're interested, but it's a little beyond the scope of the class. The point is, we have these E fields, and those E fields fundamentally are what is driving the current. That's what pushing the electric charge around, causing it to flow in the circuit. Do you have a question, Brandon?
In terms of physics, how does battery acid form?
How does it form? I mean, it's just, that's something you deliberately put into the battery. So depending on what properties you want your battery to have, you can choose different materials for that, but that's something that's deliberately put in there.
So if it's like, let's say like overused or sits there for a long time, I mean, like how does it start to like foam? Like
Yeah, that just means it's leaking out of the battery.
oh,
Yeah, right. Okay. So, do you guys remember how electric forces work? If we have an E field and we have some charge that's inside of that E field, how does it exert a force on that charge?
It goes with positive, right?
Yeah. So the force is given by Q times E, if you remember. And if the charge is positive, the force goes with the E field. And if it's negative, it goes against the E field. So remember this, F equals Q times E. If Q is positive, force is in the same direction as E. If Q is negative, it's in the opposite direction. So, the way conventional current works is we assume there's some kind of motion of positive charge in our circuit, right? So therefore, the conventional current should be in the same direction as this E field that gets set up within our wires, right? Because the direction of the force that's pushing that kind of charge around is in the same direction as the E field. That makes sense? So if we have conventional current, which assumes positive charge, the current is in the same direction as the E field that goes into this wire here. And the direction of that is it comes off the positive terminal of the battery, it loops around the wire back to the negative terminal of the battery. Okay? In reality, though, electrons are moving through the wire in the exact opposite direction. Okay, but in terms of conventional current, this is the direction things are going in. Does that make sense? The last comment I want to make about this is we're saying here that there's an E field inside of the wire that's carrying this current. And that may seem to contradict something I've said earlier about how E fields work inside of conductors. Do you remember doing these problems where we were calculating the E field inside of some kind of conducting sphere or conducting cylinder? And the assumption we always made was that E is equal to 0 inside of that conductor. That's only true in the static situation where there are no moving charges. So if there are no moving charges, you can say E is equal to 0 inside of a conductor, but this is not the static situation anymore. Here, we have charges moving around because of this electric current, so this assumption is no longer true. Okay? All right, so we're doing a lot of kind of setting the stage here. So the last thing we'll get into before we start developing some equations that can describe all of these features is the difference between DC and AC. So you probably know this difference, right? Direct current refers to a situation where the charges in your circuit are only flowing in one direction. Okay, so everything's just moving in one direction, and that direction does not change over time. So if we were to plot what DC current looks like as a function of time, it's a pretty simple situation. If on this axis we have the current I, and on this axis we have time t elapsed, the current is always going to have the same sign, indicating that we never switch directions. Okay? On the other hand, with alternating current, charges don't just move in one direction, and they can sort of slosh back and forth in a repeating pattern. So if we were to show current as a function of time in that sort of situation, we'd see that the sign does change. Sometimes the current is positive, indicating it's flowing one way, and then it switches to negative, indicating it's flowing the other way, and it can go back and forth. Now, in this case, the current kind of looks like a sine wave, correct? This is the type of current that you would get using an electrical generator. You get this sort of sinusoidal current like this. Using a battery, on the other hand, you'd get this DC current like this, where the charges are only moving in one direction. So that's the difference. So in this animation, we're seeing direct current, where electrons are moving to the right. But by the definition of our conventional current, we'd say the conventional current is to the left. Okay? If we were to look at this alternating current, it'd be doing something like this. The direction that these charges are moving just changes in an oscillating pattern, going back and forth. Okay? So for now, we're going to stick to direct currents as we analyze circuits in this chapter and the next chapter. But once we get to chapter 14, we'll start to talk about alternating current. Okay, so that will be coming up later. All right, any questions so far? Everything we just talked about is really just sort of conceptual, setting the stage.
So when we do the calculation for the amount of electrons going through a cross section, it doesn't apply to AC current, and it's just DC.
No, the definition of current still holds. It's still the case that even if you have AC current, I is defined as the amount of charge moving through a cross-section of your circuit per unit time. It's just that the direction those charges are moving in can change. But that definition is generally true. In fact, it doesn't even need to be in a circuit. You could just have a beam of electrons flying through the air and talk about what the current is. So it's a very general definition. Okay, so next we're going to cover resistance and Ohm's law. This is the topic of the lab this week, by the way. So let's get into it. So as we saw, a battery is designed to maintain a constant voltage between its terminals. And as we also saw, if you connect that battery, if you connect the positive and negative terminals of the battery to some object along a conducting path, that allows current to flow in your circuit. Okay, so for the time being, we're going to imagine this very, very simple circuit where you just have a battery, which is a constant voltage source, connected to some kind of device. We're not even going to really be specific about what this thing is. Okay? So, it turns out not every single device you connect to a battery is going to draw the same current. Okay? Some things you connect to a battery will draw a lot of current. Other things will draw less current. Depends on what type of object you connect. So this leads us to Ohm's law. For many different types of objects that you can imagine doing this for, the current that ends up being drawn from the battery is directly proportional to the voltage you apply. In other words, V, the voltage you apply, is directly proportional to I. Now, when we have this kind of direct proportionality, as always, we know there's some kind of constant that goes into this. There's a proportionality constant. And that we're going to call R. Okay, so V is directly proportional to I. We're going to write that as V equals I times R, where R is this constant of proportionality. It turns out this R constant is what we call the resistance of our object. And I'll show you why that's the case in a second. But one thing I want to emphasize here is not every single material follows this law, okay? Only certain types of materials do follow this law, and I'll try to make a distinction between those different types of materials, okay? All right, so let's just take a look at what the statement of Ohm's law really is, and then we'll get into when it applies, when it doesn't apply, and how it sometimes gets a little bit modified. So here I'm showing you a graph of current, which is I, plotted on the vertical axis, and voltage, which is V, plotted on the horizontal axis. And so what you're seeing here is different values of applied voltage. As we move along the horizontal axis this way, this corresponds to applying more and more voltage to our object in a certain direction. As we go to negative values, we're simply applying a voltage in the opposite direction, okay? But larger and larger values as we go out. So for any object, regardless of what you choose to put as your test object, if you apply no voltage, you're not going to get any current. So every one of these lines passes through the origin. And as you apply more voltage, you end up getting more current out. Okay? And if there's a direct proportionality, then all of these are straight lines. Does that make sense? But in this case, we see they have different R constants, because not all of these lines have the same exact slope, in other words. So let's take a look at the form of Ohm's law again. V is equal to I times R, right? Well, if we rearrange that just a little bit, it says I is equal to V divided by R. So in other words, if we look at the slope of this line, that's just 1 divided by the resistance, right? Does that make sense? So in other words, the object with a really big slope on this graph has a very small resistance, and an object with a smaller slope on this graph has a bigger resistance. So in this case, object number 1 has the biggest slope, and it has the smallest resistance. What does that mean? It just means we get more current out for a given applied voltage. It's less resistant to current flowing through it. You get more current out for a given applied voltage. Object number 3 is just the opposite. That has the largest current largest resistance, I should say, because even if you apply a really large voltage, you don't get that much current out. So it's more resistant to current flowing through it. Okay? That's what we're seeing in this graph. So we have this V equals IR relationship. Let's rearrange that one more time in the following way. Let's write that as R equals V divided by I. And I think this will help us understand what resistance actually means. So electrical resistance, capital R, is just how much your object opposes current running through it. Okay? So the larger the value of R, the more resistant it is to current flowing through it. And we can see that by, again, rearranging the equation to say R equals V divided by I. Because V is the voltage that we have to apply to the object. I is the current that ends up running through it. And this ratio is the resistance. So we can see that if resistance is larger, if R takes on a larger value, that means we need to apply more voltage to it to get a certain current out. Okay? If R has a smaller value, then it doesn't take very much voltage to get a large current out. Does that make sense? Let's think about units then. You may have heard of this unit of an ohm before, right? You've worked with any kind of circuit before, you are familiar with ohms. That's just the SI unit of electrical resistance. So how do we define the ohm? Well, let's just go back to this equation here. The ohm is just our SI unit of voltage divided by our SI unit of current. So 1 ohm is 1 volt per amp. And we use the capital omega symbol, the Greek letter omega, to denote an ohm. Okay, so 1 ohm is a volt per amp. All right, any questions on the units? Pretty straightforward? Okay, so that's what resistance is. Now sometimes in an electrical circuit, we'll deliberately put an object in that circuit called a resistor. A resistor is just something that has a fairly large electrical resistance. It has a large R value compared to, let's say, the wires that connect everything together. And one reason you might use a resistor is simply to control the current, right? If you increase the value of the resistance, you'll decrease the amount of current you have flowing. And the symbol that we use to denote a resistor is this right here. So let's just keep track. so far, you've seen 3 different types of symbols for things that could appear in a circuit, right? You know how to identify a battery, you know how to identify a capacitor, and this is a resistor. Okay, we'll introduce even more objects as we go, but that's just something to note here. Okay, last thing to note about resistance. Oftentimes, we'll be looking at circuits where you have different objects connected by wires. So unless we state otherwise, we're going to assume that any wires that connect different parts of a circuit have negligible resistance. So we can treat it as if R is equal to 0 unless stated otherwise for the wires that connect different things. Yes?
Yeah, I was just wondering, like, I know I've seen like resistance mentioned before, like just casual topics. Like, what's like the main purpose of inducing resistance in a system?
Right. So in a really simple circuit, you can just dial a resistance up or down. There are things called variable resistors, and by turning the resistance up or down, you can turn the amount of current you're letting into a certain branch of the circuit up or down. That's a very simple use of a resistor. If you use resistors in combination with other things like capacitors, you can vary the amount of time it takes for something to charge or discharge. There are a lot of other examples, but those are just 2 that come to mind. Okay?
Do you mean a light? An example of that or no? Like, you know, some lights at houses you can dim them. Is that an example?
Yeah, I mean, you could control the amount of current, let's say, going to a light bulb with a variable resistor. Yeah. You could even do something more complicated, like tune a radio dial with a variable resistor.
Oh,
Yeah. Or a variable capacitor. Okay, there are a lot of different things you can use this for. Okay, so we know what Ohm's law says. Ohm's law is the statement that V is equal to I times R, where R is some kind of constant. And R is a constant associated with your object that tells you the resistance of your object. What I want to just emphasize here is not every object actually perfectly follows Ohm's law. Okay? So Ohm's law, you want to think of this as an experimental result. Experimentally, if you try out applying different voltages to an object and seeing what kind of current you end up drawing, if you're dealing with conductors, like metal objects, Ohm's law works pretty well as a description of how that works. For other materials, Ohm's law does not work at all. So let me just give you an example. As we said, if Ohm's law is actually obeyed, then when you plot the current versus the applied voltage, you just get a straight line. Because I is V divided by R, and R is just some constant, so there's a direct proportionality between your current and your applied voltage. That gives you a straight line relationship. So for most metal objects, this is what you would see if you were to do this experiment. On the other hand, let's say you had an object called a diode. Is anyone familiar with a diode? Has anyone worked with these firsthand before? Diodes? Okay, what does a diode actually do? Yeah, so a diode, the function of a diode in a circuit is to let current through in one direction, but to block current going in the other direction. And so if you were to plot I versus V for a diode, it would look something like this. So for positive values of your applied voltage, this is called applying voltage in the forward direction for your diode. You would get some current out. And if you applied more voltage, you get more current out, and it would look something like this. There would be a kind of growth of the current you get as voltage increases. But then, if you go to negative values of V, you apply voltage going the other way, you essentially get no current out. You might get a small amount out, but a very, very tiny amount compared to applying positive voltages. So essentially, it allows current to flow this way, but it blocks current going the other way. And this definitely does not follow Ohm's law because it's not a simple straight line relationship between these variables, okay? So not everything follows Ohm's law, but ideal resistors do follow Ohm's law. So specifically, we want to use Ohm's law when it applies to resistors, but not other things. Does that make sense? Okay, so with that in mind, let's talk about how we can really visualize the voltage drop that occurs across a resistor. Okay, so we already established, right, that when you have current flowing in a circuit, there's an electric field present which is pushing the charges around to cause that current to flow in the first place. So let's just say that in this example that we give here, there is a conventional current, I'm showing that in blue, which is flowing down across this resistor. So as we go from point A to point B, the correct direction for the conventional current is downwards, okay? And as we know, that means there's an electric field pointing in that same exact direction. We already showed why this is the case. So there's an E field going in the same direction as the conventional current. But that's the opposite direction that electrons are actually flowing, right? Shown in red is the direction of that electron flow, which in this case would be up in the opposite direction of this E field. So does that basic picture make sense? We kind of need that picture to do the next part. So you remember how potential difference works, right? Delta V is given by the integral of minus E dot dl. So let's take this. Let's follow the direction of the conventional current going from A to B and ask what is the potential difference starting at point A, ending at point B. So if we go from A to B, are we going with the E field or are we going against the E field?
With the field.
So we're going with the E field, right? What kind of potential difference do you get when you're going with the E field? Positive or negative?
Negative.
You get a negative delta V, remember? Going with the E field because of this overall negative sign in the definition potential difference, okay? So if you follow the direction of conventional current across a resistor, there's a voltage drop. There's a decrease in electric potential if you go with the current. Does that make sense? If you go against the current, it's just the opposite, right? If we started at point B, and then we ended up at point A, then what direction would we be going in? We'd be going against the E field, correct? And what is the sign of a potential difference if you're going against the E field?
Positive.
Now it's positive, right? So if you go against the conventional current, there is a gain or an increase in voltage going in that direction. So what you need to remember here is if you're going across a resistor, if you're going with the current, then there's a voltage drop. If you go against the current, there's a voltage increase. Does that make sense? Let's do an example. Here we have a set of several different identical light bulbs. Each one has a fixed resistance of 1 ohm. If you connect 2 of these light bulbs in series to a 12-volt battery, what current are we going to get out of that? And then as a follow-up, what if we end up using 12 light bulbs? So let's work it out. So you could probably do this in your head, but I just want to draw the circuit and come up with a way of relating the voltage across these light bulbs to the voltage across this battery. Okay? So let's go through it. So I'm going to draw this using our circuit symbols. This is a battery with a positive and negative terminal like this. And then these are the 2 light bulbs, which are basically just resistors connected in series like that. Okay? And we'll call the battery voltage just plain old V. All right? Now you tell me, which way is the current going to end up flowing in this circuit? Is it going to be clockwise or counterclockwise? Yeah, current is going to flow like this. Let's try to understand why that's the case. So when we label the current like this, we're referring to the conventional current, which assumes positive charges are moving in that loop. If we had positive charges moving around the circuit, well, they would tend to be repelled from this positive electrode, move through the bulbs like this, and then back to the negative electrode. Make sense? Okay, so now let's do this. I'm going to label 2 points in this circuit, A and B. Okay? And what I'm going to do is just write the potential difference between points A and B. There are 2 different ways we could take the path going from A to B, right? We could either go across the battery, or we could go across these 2 resistors. And either way would take us from point A to B. So it should be the case that the voltage across the battery is the same as the voltage across the resistors, because they have the same starting and end points. Okay, voltage across the battery. Well, that's pretty simple. That's just V, right? And we know it's a positive voltage because we're going from the negative terminal to the positive terminal of the battery. Remember, that's how it works with batteries. If you're going from the negative to the positive terminal, there's an increase in voltage. So that's positive V, positive 12 volts eventually is what we'll plug in. Yep?
We know that because the negative sign is the little, like the smaller one.
So the reason we actually know that is inside the battery. Okay, what I'm going to try to do is draw the E field that you see inside the battery. It's going to be pointing down like this, right? From the positive terminal to the negative terminal. And so if we go from negative to positive, we're going against that E field, which is a positive delta V. That's the explanation. Okay? Okay, now let's go across the resistors. So as I go from point A to point B, am I going with the current or am I going against the current? Looks like I'm going against it, right? So the current is going like this, right? If I'm going against the current, is that going to be a positive or negative voltage? Positive, right? I'm going against the current, so we have positive I times R going across the first resistor. And then positive I times R going across the second resistor. Remember, for resistors, that describes the voltage across each one of them, I times R. V equals IR, right? But since we have 2 of those, we're going to add those 2 together. So this gives us V equals 2IR. And in this case, I want to know what the current I is equal to. So that's V over 2R. So we have V is 12 volts. That's our battery voltage. R is 1 ohm. But what is an ohm equivalent to?
Was it amps per volt?
It's volts per amp. So volts cancel out and we just get amps. And we get 6 amps in particular. Okay? Does that make sense?
So I have a question. When moving from B to A, as the drawing is showing, are you moving against the current?
Yeah, so if we went from B to A, let's do that real quick. If we went from B to A, I'd be going with the current, but then I'd be going from the positive to the negative terminal of the battery. So to have the same exact equation, just negative signs across the board, but you get the same answer. Make sense?
So just to say amperage is always positive.
I'm sorry, what?
So amperage is always positive.
Yeah, in this case, we're think of it like we're solving for the absolute value of I. Yeah. Okay. All right, now, can anyone see how this would change if we had 12 of these resistors instead of 2 of them? Yeah, so here. In this case, going from A to B on the diagram, going across the battery, I'd still just have one battery to go across with voltage V, but then I'd have 12 different resistors to go across, each one with voltage positive IR. So I'd have 12 IR in that case. So I'd be taking I equals V divided by 12R. So 12 volts divided by 12 times the resistance of each, which is 1 ohm, which is a volt per amp. So in this case, we just get 1 amp. Okay, so this is the answer with 2 bulbs. And then this is the answer with 12 bulbs.
If we had multiple batteries, our amps would go up instead of decreasing, right?
Yeah, if you had multiple batteries, then we would add the voltages together. That's right. Any other questions? Right then. So let's talk a little bit more about resistance. What resistance is, the way we define it, is how much voltage does it take to get a certain amount of current to flow through your material or your object. But it turns out the resistance can be calculated in another way. It depends on the dimensions of our object, as well as, this equation is showing up weird. Let me correct that for you in a second. As well as the material that the object is made up of, okay? So the picture you should have in mind, as far as how we can calculate the resistance of an object, is this. So we're going to have some kind of material, and then the length of the material will denote by L. And the cross-sectional area of the material will denote by A. And we want to imagine that there's some current flowing across the length of the material. So the current is flowing in the direction of L. And it's flowing through the cross-sectional area. That makes sense? So typically, we'll imagine some kind of cylindrical geometry where there's a length L and a circular cross-section A, but this is actually more general. It doesn't have to be a cylindrical object. Okay, so experimentally, the resistance is proportional to the length. So the longer the distance your current has to travel through a material, the more resistance there will be. And it's inversely proportional to the cross-sectional area A. So here's the equation that's just experimentally true. R is equal to some constant, which we'll call rho, times L divided by A. So I'm not sure why it's not showing up, but there should be an A on the bottom right here. Just take note of that. R is equal to rho times L divided by A. So again, L is the length of the material, A is the cross-sectional area. Rho is our constant of proportionality in this equation. And it turns out rho is a property of your material. It's called the resistivity of your material. So, for example, if we're using a very low resistivity material, well, we're going to get a very small value of R as a result of that. If we have a high resistivity material, we're going to get a high value of resistance out of that. So the constant of proportionality rho, let's talk about its units. The SI units of this thing are ohm meters. Let me actually just go through real quick why the units work out that way. So if R, that's our resistance, is equal to rho, that's our resistivity, times L divided by A, I want us to get some understanding of what the units of this rho constant are. So let's work it out. Rho is equal to R times A divided by L. What are the units of resistance again? So R has units of ohms, right? What about areas? Yeah, in the SI system, we'd use that meter squared units, some kind of length squared. And then L, what units would that have? Just meters, right? So the units here would work out as ohm meters. That's our SI unit of resistivity. So resistivity tells you how much electrical resistance does a given material provide. It's just a property of the material, independent of its shape and size. Okay? Okay, so that's resistivity. It's related to something called conductivity, which is given by sigma. So the electrical conductivity is simply the inverse of the resistivity. Okay, so a large value of rho means you get a very large resistance out if you use that particular material. If rho is the inverse of sigma, that means for a large value of rho, you have a very small value of the conductivity. That just means it doesn't conduct electricity very well. Okay? If you have a small resistivity, on the other hand, then you have a very large conductivity. And that type of material does conduct electricity very well. So that's the idea behind these two things. All right, here's one for you to work out. So suppose that you want to connect a stereo to two speakers, and the wires that you're going to use are 20 meters long to connect the speakers to the stereo system. Let's also assume that these wires are going to be made from copper. And I'm just going to give you right here the resistivity of copper. It's 1.68 times 10 to the minus 8 ohm meters. So let's say you want the overall resistance of each one of those wires to be 0.1 ohms. How thick should you make the wires? What should the diameter of those wires be to achieve that resistance? Okay? So answer that first. Then, as a follow-up, let's say that the current flowing through these wires to each speaker is 4 amps. What is the voltage drop across each one of those wires? So find the diameter using this equation that we just came up with, and then find the voltage drop using Ohm's law. And then we'll go through it together. So take a few minutes, see what you get. Find the cross-sectional area A, and then you can use that to get the diameter of the wire. Does anyone have the diameter? What was that?
0.0.2.
Meters? So yeah, about two millimeters around that kind of diameter. That's right. Let's go through this real quick. So when it comes to a wire, you can assume a cylindrical geometry. Almost every single wire you're ever going to encounter has a cylindrical shape where it may be very long compared to its diameter. But let's just be clear, the diameter is the end-to-end distance here, okay? And the cross-sectional area would be the area of that circular end cap right there. So our electrical resistance for this wire is the resistivity of the material, rho, so that simply depends on the material that's used, times the length of wire divided by the area A. So in this case, we're going to find the area. Okay, A is going to be equal to rho times L divided by R, correct? So let's just plug in what we know. We're using a copper material, so this is resistivity 1.68, 10 to the minus 8, ohm meters. So it just so happens that the length that's required is 20 meters, so that's L. And the desired resistance is 0.1 ohms. So we can see that unit-wise, this comes out in meters squared. So that makes sense, given that we're finding an area. So what is the area? Could someone give me that?
3.36 times 10 to the negative 6.
3.36 10 to the minus 6 square meters. So of course, it's a tiny area compared to a square meter because wires tend to be quite thin. Square meter is like the area of one of these desks up here. So, okay, how do we go from that area to a diameter? What should we do? Well, first we have to use A equals pi r squared, right? It's a circular area, so it's going to be pi times the radius squared. So the radius would be the square root of A divided by pi. Okay, because it's a circular area, we can use this formula. So we'll take the area we found, 3.36, 10 to the minus 6 square meters, and we'll divide pi, and then we'll take the square root of that. And what does that come out to right there?
That was 0.00103 meters.
Yeah, this is 1.03. I'm going to do this in scientific notation, 10 to the minus 3 meters. We keep 2 sig figs if we just follow through from where we started. Okay, the diameter is 2 times the radius. Okay? And the radius is, about 10 to the minus 3 meters, but that's a millimeter. Okay, so I'm going to write this as 2 times 1.03 millimeters, which comes out to 2.06 millimeters, or roughly 2.1 millimeters. So that would be the diameter of the wire that's required for us to get this resistance. Does that make sense? So we increase the diameter, we increase the area, will give us less resistance. All right, the voltage drop, that's pretty straightforward. The voltage across the wire is just given by I times R. And the current I is 4 amps. And what's the resistance? 0.1 ohms. Again, tell me what that equivalent unit for an ohm is. It's volts per amp, right? So that gives us 0.4 volts across the wire itself. Okay, any questions on this? Right then. So let's do some more examples. Actually, there's one more thing to say about resistivity here. I forgot I was going to say this. So resistivity, rho. Okay, it's a numerical factor that goes into our calculation of electrical resistance, and it's a property of a material. Okay, as we saw, the resistance of a certain object, like a wire, let's say, it depends on its length and its area, as well as the material it's made from. But resistivity is just a property of a material. Okay, it's just a property of the material alone. So we can classify different materials as either being insulators or conductors depending on their resistivity values, okay? Because generally speaking, anything with a very low resistivity, we can classify as a conductor, and anything with a high resistivity, we classify as an insulator. Now, this isn't such a neat classification system, but for the most part, it's going to work for our purposes, because metallic objects are going to have very low resistivity and be classified as conductors, and essentially everything else is an insulator. There's some exceptions to this, but that's going to be a good enough picture for now, okay? So let's take a look at this table to help guide us along. I know the table is a little bit small. You might have trouble reading this, but we see copper right here. The resistivity value is given as 1.68 times 10 to the minus 8 ohm meters. If we look at silver, that has a slightly lower resistivity. If we look at other metals like gold, aluminum, those all appear here. And they're in the same ballpark as far as resistivity goes. Something like 10 to the minus 8 ohm meters. Okay, so that's what we're talking about for conducting materials. If we go further down in the table, what do we have for glass? What does this say? Yeah, kind of depends on the type of glass you use, as it turns out. But 10 to the 9th power, all the way to 10 to the 12th power ohm meters for that material. Or rubber, even more, right? 10 to the 13 to 10 to the 15. So we're talking over 20 orders of magnitude difference between conductors and insulators. That's a pretty substantial difference, right? So it's a pretty clear distinction between these types of materials. But there's a slight complication to this. So experimentally, the resistivity of a material can change. And in particular, it can change with temperature. As you heat up an object, you tend to increase its resistivity. So rho tends to go up as you increase the temperature. So we're going to see the reason for this in the next lecture when we talk about the microscopic view of electric current. But for now, let's just take this to be an experimental result that we can use, okay? This equation describes how resistivity depends on temperature. So it's a pretty straightforward relationship. The idea is we're trying to calculate the resistivity by plugging in the temperature. But what we start with is the resistivity, which we call rho naught. Rho naught is the resistivity of our material at temperature 20 degrees Celsius. So 20 degrees Celsius room temperature is what we call our reference value of temperature. We know the resistivity at this temperature, and we'll use that as a baseline to calculate the resistivity at some other temperature, okay? So rho naught is the resistivity at this reference temperature. Rho is the resistivity at some new temperature that we want to calculate. And we'll call that T. Okay, alpha is something we call our temperature coefficient of resistivity. So here's how it works. Rho, the resistivity we want to calculate, equals rho naught, the one we already know, times all of this, 1 plus alpha T minus T naught. So let's just kind of see how this equation functions. As T goes up, hopefully you can see the resistivity is going up, but it also depends on what this coefficient is. If alpha is bigger, then your resistivity grows really quickly as temperature goes up. If alpha is smaller, then your resistivity doesn't grow that fast as temperature goes up. So that's how the temperature dependence works. Any questions on that? All right, so let's keep going. Let's do this example. the tungsten filament in a light bulb reaches a temperature of about 3,000 degrees Celsius when current flows through it. That may seem hard to believe, but yeah, the filament inside of a tungsten light bulb actually does get that hot when it's glowing at its full brightness. Now, of course, that's a lot hotter than room temperature, which is about 20 degrees Celsius. So the question that we want to answer is, compared to room temperature, which is 20 degrees Celsius, how much does the resistance of the filament increase when the bulb gets up to this operating temperature? So let's work it out. Here are the things we're going to need to know. For tungsten, the alpha, the coefficient, temperature coefficient of resistivity is 4.5 10 to the minus 3. The units here are inverse degrees Celsius. Rho naught is 5.6 10 to the minus 8 ohm meters. That's what the resistivity is at 20 degrees Celsius. Okay, so that's what we know about tungsten. Let's use that to figure out how much the resistance is going to increase by increasing the temperature by this much. So let's work it out. So here we go. The resistance of our tungsten filament R is going to be given by the following. It's going to be given by rho, that's the resistivity of the material, times L divided by A. So presumably, the length of our tungsten filament is going to stay the same, and the area is also going to stay the same. That's not going to be affected by this increase in temperature. But what is going to change is rho, okay? Now, how exactly does rho change? Well, rho is given by rho naught times 1 plus alpha T minus T naught. So that's just the substitution I made right there. And that's multiplying L divided by A. Does that make sense? So to shuffle things around just a little bit, I'm going to write this as rho naught times L divided by A, just sort of group that together, times what's in the brackets, 1 plus alpha T minus T naught. So this set of constants out front, what is that? That's the resistivity at 20 degrees Celsius times the length of the filament divided by the area of the filament. Well, that's what we could call R naught, the resistance at temperature 20 degrees Celsius. So this whole thing in front is our resistance at 20 degrees Celsius. What we get out of this calculation is the resistance at some other temperature. We can choose to plug in any temperature we want. So here's what I'm trying to find. R divided by R naught. Why is that? Because I want to know by what factor did the resistance increase. So if R divided by R naught is 2, then my resistance doubled. If it's 4, it went up by a factor of 4. What I really want is that ratio of R divided by R naught. Does that make sense? So that's just 1 plus alpha T minus T naught. Because I'm dividing out this part. Okay? So here I have 1 plus alpha for tungsten. That's 4.5 times 10 to the minus 3 inverse degrees Celsius. Okay, T, that's our operating temperature of 3,000 degrees Celsius. And T naught is our room temperature, which is 20 degrees Celsius. So this is what we're calculating. Can someone crunch those numbers real quick and tell me what it comes out to? Can you say it again?
14.4.
Yeah, that's right. So the resistance will increase by a factor of over 14 when you heat it up in this way. Okay? Any questions on this? Okay, so we'll keep going. Here's a question for you. You may wonder how these digital thermometers work. If you've ever used one of these to measure your own body temperature if you feel sick, or you can use this in a kitchen to measure the temperature of like water or something you're cooking. We're talking generally about a digital thermometer. So the way these things can work, one way to design them, is to use the variation in electrical resistance that comes with a change in temperature. So as the temperature changes, electrical resistance changes, and if you can measure that change in resistance, you can measure the temperature. That's the idea. So let's say that this is the situation. We have a thermometer that consists of a strip of platinum, which at room temperature has a resistance of 164.2 ohms. So that's what the resistance of this strip of platinum is at room temperature, 20 degrees Celsius. But if we place this thermometer in a cup of hot water, we notice that the resistance increases to 187.4 ohms. So the question for you is, what is the temperature of the water? So we know the resistance at room temperature, we know the new resistance. So what is the temperature that corresponds to that resistance? To do this, you're going to need to know the temperature coefficient alpha, which is 3.927 10 to the minus 3 inverse degrees Celsius. So try to work this out, see what you get, and then we'll go through it together. You can use the previous problem as a starting point. Okay, let's take a minute to go through this. Does anyone have the answer?
56 degrees Celsius?
56 degrees Celsius, that's right. So, again, we can use the previous problem as a starting point. We said that resistance at some temperature is equal to resistance R naught at room temperature times 1 plus alpha T minus T naught. where T is your new temperature and T naught is your room temperature. So we're just solving for T here. So first thing we can do is divide out the R naught. So R divided by R naught is 1 plus alpha T minus T naught. Why don't we subtract this factor of 1? So we'll have R divided by R naught minus 1 equals alpha T minus T naught. Next, let's divide out that factor of alpha. So we have T minus T naught is R over R naught minus 1 divided by alpha. And then finally, let's add the T naught term to both sides, and then we just have T equals T naught plus R over R naught minus 1 divided by alpha. So we have 20 degrees Celsius for T naught. Okay, R, that's the resistance after the platinum's been heated up. So that's 187.4. Sorry, that should be a plus sign. R is 187.4 ohms. R naught, that's the resistance at room temperature. That's 164.2 ohms. So that's R over R naught minus 1 divided by alpha. Alpha is 3.927, 10 to the minus 3 inverse degrees Celsius. Okay? And of course, that becomes degrees Celsius when we divide it out. So what do we get? We get 56 degrees Celsius. You can verify that just by punching these numbers in. Any questions? So that's a practical use of this idea. Again, if you can change the resistance, you can change the electrical properties of some material in a way that is dependent on temperature, you can use that as a way of measuring the temperature. All right, so the next topic we're going to get into, which will just start today and then finish this up on Wednesday, is electrical power. So can you remind me, in physics, what do we mean by power? What is the definition of power? Yeah, it's basically a rate of energy consumption is a way of thinking about it. It's energy over time. And depending on the context, power can mean a lot of different things, but I guess the most general way to say it would be energy per unit time, right? So in physics terminology, when we refer to power, we're talking about the rate at which energy is being consumed. Or another way to say it is the rate at which energy is transformed from one type to another. So, if we were to take this to be an average value, so what is the average power in some time interval, delta t? We would take delta E, the total amount of energy transformed in that interval, divided by delta t. But if we were to take the limit where delta t goes to 0, then we'd be talking about the instantaneous value of power. So what is the rate at which energy is being consumed right at some instant in time, as opposed to an average over many different times? That's given by dE dt, the derivative of energy with respect to time. Okay, what about units? We know the SI unit is a watt. Okay, remember, a watt is defined as a joule, which is our energy unit per second, which is our time unit. Okay? So let's take a look at a few examples of how this definition of energy transformed per unit time applies in some different cases. So an electric motor, that's something we're going to learn about in an upcoming chapter. We're going to actually understand the physics behind it. But what a motor is doing in terms of its power is converting electrical energy into mechanical energy. So you run current through the wires of the motor, and that's transformed into mechanical energy because the motor starts spinning. Okay, we have an electric heater. We're also starting with electrical energy, but in this case, we're trying to convert it to thermal energy to heat up some, volume of space. Okay, if you pay your electric bill, you're familiar with this unit, right? Kilowatt hours. So a kilowatt hour is actually not a unit of power. A kilowatt hour is a unit of energy. Okay, a kilowatt hour is an amount of energy. And here's how we can think about that. If we take the definition of power, okay, and rearrange it to solve for E, we have delta E is equal to P times delta T. So the way you want to think about a kilowatt hour is this. The power is a kilowatt. So that's the rate at which you're consuming energy, is a kilowatt. But you do that for a time interval of 1 hour. And when you multiply those two together, you get a kilowatt hour. So 1 kilowatt times 1 hour is a kilowatt hour. That's the way you want to think about it. And as you can see, it's a unit of energy. So it's a way of just totaling up how much energy you've used in your household. Okay? And that's what you get charged based on. Any questions on that? All right. So question for you. How many joules of energy are in a kilowatt hour? So start with a kilowatt hour. See if you can convert that over to joules. What I would do is just expand out kilowatt hours. Just how do you expand out kilowatts into more basic units of joules and seconds? So one more zero there. Okay, so I see some of you have this already. How many joules in a kilowatt hour?
3 times 10 to the 6.
Yeah, 3.6 times 10 to the 6, actually. But yeah, I think that's what you meant. So how do we do this unit conversion? Well, remember, a kilowatt hour is literally a kilowatt multiplied by 1 hour. As this follows, delta E equals P delta T. Okay? Okay, unit prefix kilo. What power of 10 does that refer to? That's 10 to the 3. A kilo is the unit prefix equivalent to 1,000 or 10 to the 3. And then what is a watt equivalent to?
1 joule per second.
That's a joule per second. Okay, so if we could just convert hours over to seconds, then you would see that the seconds would cancel, you'd just be left with joules, right? So, okay, how many seconds are in 1 hour?
3,600.
3,600 seconds is the same as 1 hour. So now we're at joules, and you're right, this comes out to 3.6 10 to the 6 joules. So when you see a kilowatt hour of energy, you know what that's equivalent to in the SI system. All right? That's it for today.